Yeah, so this talk would be on, we saw some excellent talks in this workshop, so I would like to thank the organizers first. So yeah, I was hoping I would give a slide talk, but after seeing so many excellent board talks, I thought, yeah. Well, the real reason is also I couldn't finish my slides by this morning. So anyway, so okay, so the talk would be on a lower bound for homogeneous depth-4 formulas, and it's a joint work with Neeraj, Newton, and okay, so please feel free to stop me anytime if there is any confusion. Yeah, part of this talk would be more on, what we, or rather I don't understand about shifted partial measures, especially the question as to whether there is any hope of proving more lower bounds, stronger lower bounds, or lower bounds for more general models of computation using shifted partials or any variant of it. So I won't be going into too much of calculation, so it's but please feel free to stop me. Okay. Right, so just a brief recap of what we already, sorry. Oh, a little bit, oh, sure, sorry for this. Right, so a brief recap of what we already saw, and it's along the same line of proofs and ideas and techniques that we already saw in these two papers. One is by Ankit, Neeraj, Ramprasad and Pritesh. The other is this FLMS paper, which Srikant discussed in the morning. And the summary of this is the following, that we know, or we could prove, to the omega d by t lower bound for the following model, which I denote by this. So just to make the notation precise, so here's the notation, and this I'll try to follow uniformly. So n would be the number of variables, d, which is typically polynomial in the number of variables, is the degree of the target polynomial. By sorry about this, I should write bigger, right? Okay. Right. So, and by this, I actually mean it's the same thing, the homogeneous depth-4 formulas where the bottom pi gates, their fan-ins are bounded by t, right? Okay. So this was discussed by Ankit the other day, and this morning Srikant showed that, and here the target polynomial was determinant or permanent. Right, so, and this was improved to the following lower bound of for the same model, and here the target polynomial was the iterated matrix multiplication polynomial with the dimension of the matrices being n and the degree of the or the number of matrices being b. So here t, the relation between the number of variables and so roughly, because we are just looking at the 1th entry, so it's roughly this. Okay, good. Right. So what's so nice about this line of results, especially at this frontier? What's so nice is that it basically shows that if you look at the reduction from poly-n-sized circuits to the special kinds of depth-4 circuits, this reduction is tight in the sense that, so let me also write it, so that one common thing about both these lower bounds are both are top fanning lower bounds. Okay. So, and we also saw this result of this, right? The reduction from poly-n-sized circuits to sigma pi t circuits or formulas with top fanning 2 to the order d by t log n. So this result actually shows that this reduction, this particular reduction to this kind of model is tight. So which is nice, which is very nice to know. Right. And it not only shows you for circuit, it actually shows you for special kinds of circuits which we know by the name ABP. And just to refresh the relationship between these different models, so we have homogeneous formulas here. Which is captured by ABP, and that's captured by poly-sized circuits of small formal degree, which we also know by the name VP. And on top of all this, we have the class VNP of polynomials. And the outstanding open question here is whether this is true or not. And at the same time, whether any of these containments is actually tight or not. So let me also write it. Right. Correct. So yeah, so this is just to refresh the relationship between the different models. So coming back to this point that this reduction is actually tight as far as this model of depth-4 circuits is concerned. Okay. So what does this say actually? This says that, so you remember in the last talk, Srikant mentioned these 2 points, that in order to prove better lower bounds, you can possibly think of these 2 different ways. One is a better reduction to possibly this kind of circuit. So to prove, let me write super poly lower bounds for general circuits, you can go by these 2 ways. A better reduction or possibly a better lower bound for already known models, maybe using whatever measure, using shifted partial or something else. So this result basically rules out part of this first option. I say part of this because it rules out only for a better reduction for this model. Right? I mean, there can be possibly other kinds of reduction to other special kinds of depth 4, for which maybe it's possible to prove a lower bound via shifted partial or something else. Okay? So I would still say that both the options are not entirely closed. I mean, they are still open to a significant extent. Right? And another thing I want to point out here, okay, maybe I'll go to it later on. So the natural question is, but even if I'm willing to believe that maybe the shifted partial measure is not powerful enough, just like it in the present form, to separate VP from V and P, even if I'm willing to believe that, there are also interesting questions, like can you separate homogeneous formulas from ABP? And these questions are also by themselves very interesting, and each of these questions, if resolved, would lead to significant progress for the field, right? So, and Ami Yahudov actually mentioned the separation result between ABP and formulas in the multilinear case, that multilinear ABP is different from multilinear formulas. Right? There's a super polynomial difference. So indeed, I mean, even the other questions are also quite interesting here. And one question would be that, fine, okay, can you actually prove a super polynomial lower bound for homogeneous formulas, right? Using shifted partial or maybe a suitable variant of it. Right. So let's write this question. That's the main question that would be the motivation behind this talk. Can we prove super poly lower bound for homogeneous formulas? Now towards this, there's one modest step taken by few people, leaders and others. It shows the following. It actually proves super poly lower bound for very special kinds of homogeneous formulas that they called it regular formulas. It proves a homogeneous super poly lower bounds for you can think of, at least for this talk, you can think of regular formulas as some very natural subclass of homogeneous formulas. So what are they? So they look like this, that it's alternating layers of addition and subtraction gates with basically one restriction. And that restriction, it's still smaller, is it? Oh, sorry about that. Yeah.
Yes, better if you would write a bigger because the video also
needs to. Okay. Yeah. Maybe I'm trying not to erase the board too many times. That's why I'm using small font. But I will. Okay. I'll try at least. Okay. Right. So these are special kinds of homogeneous, special but natural kinds of homogeneous formulas with the restriction. So it can be of any depth, with the restriction that if you look at any particular layer, all the fan-ends are the same. And the degree of the formal degree is not too large. It's the formal degree of the polynomial is roughly, let's say, some constant times the actual degree of the polynomial which it is trying to compute. Now, I say it is natural, not because it just looks natural. It has some significant computation power. You can show actually, and these are like pretty, I think part of the proof was already shown by Srikant, that you can start with a poly-sized ABP and you can convert it into a regular formula. The size is not too large. And it's not just ABP. If you start with a poly-sized circuit, again, you can convert it to regular formulas. Of this much of size. So it's not that it doesn't have significant computation power, I would still say that this is small compared to exponential size circuit that we usually see around. So it's a natural question whether we can prove lower bound for this model or not. And turns out that it could show lower bound on this, but using this uses the shifted partial measure as it is. Whatever we saw in Ankit's talk and Srikant's talk this morning. Right, so good. So let me at least give you a proof idea of how this goes. This basically takes the first root. It shows that if you start with a small regular formula, you can squash it to a depth-4 bounded fan-in formula, whatever that model is, with somewhat small top fan-in. And this actually gives a lower bound. Since you already have a hard polynomial for which you know that the top fan-in will be large, and if you start with a regular formula, squash it down, the top fan-in is small, that gives the separation. So the separation goes via the first root. But it's a direct thing. You start with it, compress it, direct computation. So let me write it down here. So what it shows is proof. If you start with a small sized regular formula, it directly, so for the moment allow me the term direct reduction. I'll try to qualify what I mean by direct reduction to a sigma pi formula of small fan-in, little o of top fan-in. Right. So, and since this happens, that's why you get a super polynomial lower bound for it. So the natural question now is that, oh fine, we have a super polynomial. Yeah. So, which one? Size of? Oh yeah, we started with some poly and size regular. Log of capital N, which means log size. Yeah, you can think of that. Yeah, let's say size is. You can think of it. Yeah, thanks. Right. So the natural question now here is, are we there? I mean, if our motivating question is proof of super polynomial lower bound for homogeneous formulas, and we have proved the super polynomial lower bound for regular formulas, can we now show that every homogeneous formulas can be computed by a small sized regular formulas? That means regular formulas captures homogeneous formulas tightly. Can we show that? So, if we could, for a moment if I think that if we could, then if you add the result which Srikant covered this morning, shows that ABP is hard for, or IMM, which are the same, is hard for this model, this model. And now, if for a moment I am willing to believe that regular formulas is the same as homogeneous formulas, then that would give actually a separation super poly separation between ABP and regular formulas. So this, along with this, gives a super polynomial separation between ABP and regular formulas. Now, if regular formulas are the same as homogeneous formulas, that would immediately imply that, okay, we have done something, have taken some nice step in this, in arithmetic circuit complexity by separating ABP and homogeneous formulas. But it turns out that this is not true. And that's a very nice result by Mrinal Kumar and Shubhangi Saraf. They actually showed that by the same argument, they showed, I should not say by the same argument, by using the same measure, which is shifted partial, but a completely new and novel argument. Super polynomial separation between homogeneous formulas and regular formulas. So I say that the strategy is the same because the way to prove it is by showing that as far as this model is concerned, you can even pick up a homogeneous formula and show that it is a hard polynomial as far as this model is concerned. By hard polynomial, I mean that there is a, okay, I'll make it formal. Okay, so the strategy is the same. You start with a regular formula, squash it to a small size, this formula, and then show that there is a homogeneous formula which will take large size. By size, for the moment, I mean the top value. But what is a bit alarming at this moment for the shifted partial measure is they not only separated homogeneous formulas and regular formulas, they actually separated homogeneous depth-4 formulas. And that's a bit alarming, I would say. Which basically, they say that there are homogeneous formulas such that if you somehow, try to reorient the formulas and make it a formula like this with bounding bottom finance, then it will take large top finance. Okay? So there's, in fact, a separation there itself as far as this model is concerned. Okay? So just to, a slightly formal statement. There exists a family of polynomials computed by poly n size homogeneous depth-4 formula such that for almost any t within these two large ranges, maybe some epsilon n and I'm not sure, maybe log square n, very large range, for any t here, any sigma pi t formula computing Qn must have top finance Okay, so that's the separation between homogeneous formulas and regular formulas. So although it looked quite clear. Yeah, it's alarming because now I know that if I want to prove a lower bound for homogeneous formulas using just a shifted partial method via using this sub-result that when the bottom finance are bounded, then we already have a lower bound, then there's a problem. We can't because already there are homogeneous formulas. It's already hard. So you should try to separate these two models using the roots taken by Kayal et al. And Kumar Saraf, then there's a problem. Right? So direct reduction won't work. Am I clear? In case there's any question, please stop. So the moral of the story here is it rules out the possibility of a direct reduction from homogeneous formulas, depth-4 formulas, to homogeneous, that particular kind of formulas. Formulas of small top. right? So now what to do? Now, at this moment, I think this is the right time to qualify this, what I mean by a direct reduction. So, see, all this prior work, the way they were proving lower bound, was they were starting with some model and showing that whatever polynomial is being computed by this model, the same polynomial can be computed by this smaller sigma pi sigma t model. So that's a direct reduction. Start with this, compress it. It's talking about the same polynomial. But one could possibly think of some kind of an indirect reduction. Let me make it a little more precise. So suppose C is this. Let C be a homogeneous depth-4 formula. Now, it is conceivable that C might not exactly be computed by a small Ct, where Ct looks like this. Ct is exactly like this. Ct is this kind of formula. But maybe along with some other polynomial which actually helps in the computation, but I write junk because of the following reason. So let me write it. It is conceivable. I'm not saying it will always happen. Sometimes we are lucky, it might happen. So where this is a sigma pi t formula of size same or comparable as C, such that the following happens. If with this setup so by subadditivity, I mean this property that mu of whatever that measure is, f plus g, is bounded by mu f plus mu g. Okay, such that mu of C junk is 0, let's say. So then what happens? If you try to apply mu in this equation, you get mu C, which is by subadditivity, I can say this is bounded by this plus this, and since this is 0 by assumption, the upper bound on Ct still gives an upper bound on C, right? And if you recall the lower bound proofs using the shifted partial method, for a moment if you think this is a shifted partial method, the way we were doing proofs in Ankit and Srikant's talk was you first prove an upper bound on this, and then you prove an upper bound on some hard polynomial when you apply the measure, and that gives a lower bound on some hard polynomial, and that gives a measure, the lower bound, the ultimate lower bound. So basically, I want an upper bound of this measure when applied to a circuit. Right? I'm saying that if such a thing happens, then already we have an upper bound. Although there is no exact computation, I'm not saying Ct is exactly computing C. Computation-wise, C junk is important. But when you apply the measure, C junk is not important. So that's the main point here. Okay? So, right, so now the question is that how can we do this? So how can we ensure this? And we also need to ensure subadditivity. Okay. So to understand this, I think the best thing to do would be to understand with an example. The same example which actually led us to a proper mu that works. And the example has already been covered by Neeraj in his talk and Srikant in his talk. So it's on homogeneous depth-3 circuit. Lower bound for homogeneous depth-3 circuit. So I'll just quickly refresh what they say, that if C is a homogeneous depth-3 circuit, it's basically a product of linear forms. Like these. And so I'm just refreshing the proof done by Srikant here. So suppose you want to define a measure. So I define a partial derivative measure like this. It's a dimension of, so I have this target polynomial in mind, which is the iterated matrix multiplication, and you look at the alternate layers of matrices, d by 2 of them. You're only going to take derivatives by picking one variable from here, one variable from here, one variable from here, like d by 2. So these are the shaded regions with respect to which I'm taking derivative d by 2 of them. And let's call this layers, this shaded layers, as, let's give it a name, let's call this S. So the measure is you take all possible multilinear derivatives by picking one variable here, here, like this, which naturally gives the order of the derivative to be this of your whatever polynomial. So that is the partial layer. The usual, we all know this by now. Okay, and he showed that this for the IMM, P of D for the IMM is actually n power d. Or let me just write over d. Okay, because every such derivative will give you a different monomial. All of them are distinct. Each layer has n square variable. There are d by 2 of them. If you just take all possible derivatives, that will give you distinct monomials, and that's this. On the other hand, if you look at PD of the circuit, this measure obeys subadditivity. So that's less or equal to S times PD of one such product and this we also know that when the derivative is applied on this, it basically acts on d by 2. It chooses d by 2 of the linear forms and acts on them. Right? So that naturally gives you S d choose d by 2, which is S times roughly 2 power d. Is this work clear? I'm just recalling the earlier things. That's all. You're just picking d by 2 of the linear form. Okay. Which gives a lower bound on I. Okay. So now for a moment, let me use the same setup. So think of the following one. Suppose you see now is sum of where each Qij is a sum of univariates. By this I mean it looks like f1 x1 dot 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 to fn xn. I'm not saying anything about the internal degrees of this. It can be anything. A linear polynomial is a special case of this, where each of them is just a variable. So internally, let them be anything. But the outer degree I restrict to d. Now I ask the same question. Can I show a lower bound for IMM on this model? It's a toy model, but it just gives you a motivation. as to how one might go about changing the shifted partial measure a little bit. So let's see. So it's clear that since the ultimate target polynomial is multilinear, the higher degree monomials ultimately cancels out. But I just can't throw them away right away, because we all know by now that of this beautiful paper of Chasm at depth-3 that it loses homogeneity. It goes to some humongous degree, but somehow some magical cancellation happens at higher degree monomials, and ultimately the determinant is computed by a small size, reasonably small size depth-3 circuit. So I just can't, throw larger degree monomials right away, because they actually help in computation. But let's see, measure-wise, we might be able to do it. So that's the point. So let's see how to do it. I want to use this over there. So you see that Qij, which is So let me say that Qij looks like a linear polynomial plus some supposedly junk part, which is basically the degree greater than or equal to 2 part. It's Qij, right? So which means that C, if you expand it out completely, it will look like plus some C junk, and this C junk has the property that I got this by multiplying the Qij's using this relation. If you look at any summand in Q junk, it looks like any summand in C junk looks like some Jij times something R. It must involve at least one Jij, right? Okay, good. So I want to use this fact, the fact that Jij is present, to actually cancel it off after applying a measure on both sides. Okay, so let's see what could be a suitable measure. So it's immediate that this has large degree. So one clue is maybe a projection should involve multilinearity. Okay, so let me define, allow me to carry forward this tuition and define the projection like this. When it takes F and it maps to just its multilinear part. And then, well, this is enough, but just to make the proof slightly simpler, I'll do one little more thing. I'll also set all the variables S to 0. All variables x equal to 0, where x is in S. You remember the S was a set of variables here in the shaded regions. Okay, that's S. So after projecting into multilinear parts, you set those variables to 0. Okay, now let's see. Now I define this new measure. Let me call it slightly altered. Altered partial derivative. Projected partial derivatives, let's say. So, and the measure here is the following. It applies the map, let me call it PPD, projected partial derivative, of F. It applies the projection map on top of the partial derivative map. Okay, so is this clear? Okay. Earlier it was just this dimension of the set of all derivatives. Now you apply this projection on the derivatives and then look at its span and its dimension. Good. So now let's see. First, what happens to this polynomial? The claim is this is the same as before. Nothing really happened. As far as the target polynomial is concerned, this measure is the same. Because if you think of the target polynomial, after taking derivatives, these variables are not there at all in the polynomial. So even if you set them to 0, nothing happens. And after taking derivatives, everything is multilinear. So this projection acts as if it's not there as far as the target polynomial is concerned. Right? And this is a crucial thing. Is this clear? Okay? So now let's see. Now, let's apply this measure on the circuit. You can notice one thing which I kind of hand wave, that even with projection, it obeys subadditivity. The reason being that a projection here, this measure obeys subadditivity. The reason being, if you want to apply a projection on f plus g, that's exactly projection of f plus a projection of g, the way we have defined it. So it obeys subadditivity. So I can easily write this as of the C-jump part. The claim is this is 0. Equal to 0. Let's see. Now I know if I expand C-junk, every summand will have this, will look like this. It has one J term. So let's try to do a quick proof of this. So PPD of C-junk by subadditivity will be a long summation PPD of each of this, right? I don't care about the summation. I will show that each of them is 0. Okay? So, and since this is a positive thing, it's a dimension, it's a positive thing, this less than equal to 0 means it's 0. Fine. So, right. So why is, let's try to understand this. So I'll forget the index, it doesn't matter. But just remember that J is the degree greater than 2 part. And some other things, I don't care about it. It's the dimension of, we apply the derivative on GR. Right? Okay? So, right. Remember J is a sum of univariates. We took the degree 2 parts from it. J came from Q. So J itself is a sum of univariates. Sum of univariates of degree greater than equal to 2. Right? So the moment you take one derivative, if it acts on J, it will reduce it to just a univariate. So you can't apply another derivative because these are multilinear derivatives on distinct set of variables. So if you apply, you have to apply it once. Otherwise, it remains. Okay? For a moment, forget this. You just expand the derivative, the long sum. On some of the j's, the derivative acts. On some of the j's, it doesn't. Okay? And since, but think for a moment, what happens when a derivative acts on this? If it's on the same variable, it has degree 2. It can reduce it to a linear polynomial. And that linear polynomial has no constant term. Yeah, because I have started with j, everything being greater than or equal to 2 degree. If you take a derivative, it can only go to something times x. Nothing more happens. Right? And now, if that happens, this projection map kills it. Because this, along with multilinear of f, it also sets those variables in S to 0. Are you following? Right? Is this part clear? If there is a variable in S where the derivative is acting on J, it reduces it to a univariate polynomial where the variable there is a variable in S. So when the projection acts on it, it kills it. Because there is one variable left. And if it doesn't act, then already it has degree 2. Then the multilinear component of the projection kills it. So together, the multilinearity as well as x going to 0 for all S all variables in S together, this projection and the kills everything here. Is this clear to everyone? And that means this is 0. So,
what is the degree 1 part get killed?
the degree 1 part gets killed because the projection, if you look at it, it also sets variables. It also sets variable in S to 0. And when you take a derivative, you are taking derivative only with respect to variables in S. So, if it reduces to a linear part, it's a linear polynomial in a variable in S. So then, that thing kills it off. So these two together kills it off. Okay? So, right. So, and now you see that what happens now is PPD of C is basically PPD can be bounded by just this, which by subadditivity I know that it's of just one polynomial. And for this, it's easy to see that this is always d by the same as before. Sorry? Y is the same as before. So PPD of L1, it's an upper bound, so it won't matter, is dimension of the projection map of this, right? So again, when you take derivative, it's like choosing d by 2 out of them, and then the projection, it can only lower the dimension. Okay. Okay. Shall we do it with an example?
Only one form. X1 plus x2 over x7 is squared. You take the derivative equal to x1, you get summation of xi. Now you project the next one equal to 0, you get x2 after x7. You take the derivative equal to x2, you get a different thing. So dimension 1, you get dimension 2.
Right. So let's do it with it.
Just take any basis of just the partial derivative of the derivative. Take any basis.
So,
for the moment, suppose you project the projection of x. No, all the projection exists. No, but without the projection, there is some basis, say G1 through GR, where R is D through D present. Right? Before the projection. No, but only the simple number, many different S's will be the same projection. Then the instructions will be all the only thing I'm saying is that if I have some vector space on polynomial that has the basis D1 through DR, then it's the same S.
yeah, same is, yeah. S is same. S doesn't vary. S is fixed. It's a fixed linear.
So that's just fixed.
Pi.
It's like the same pi and S must be the same value to take the derivative. So whenever we take a different derivative, we take a different S.
No, S is just all the variables. All the variables in all the variables.
Right. So, yeah, so sorry for the confusion. So it might happen. So let's take this example. So suppose this happens. So derivative might be with respect to, let's say, right. So it might be that the derivative picks one variable from it here, but when, right. Sorry for the confusion. I understand this might confuse. When the projection is not on just this variable, it's on all variables in S. So it's a uniform projection. You're right. Otherwise, it won't happen. Yeah. Okay. So forget about this. This means it picks d by 2 variables from the shaded layers, which I call S, denoted by S, and it takes the derivative. And this means set all variables in S to 0. S is fixed. Yeah, so it might, so the diagram is there, so it might happen. So it might happen. No, sorry, sir. So it might happen that x1 is here, x2 is here, and you take d by 2 of them, and x d by 2 is here. But there are also other variables. So taking derivative with only respect to these variables doesn't mean you are only setting these variables to 0. You are setting everything to 0 here in all the other layers after taking derivative. So the outer projection is uniform on whichever derivative you pick. Right? The derivative, can be taking a different d by 2. Okay. So and now this happens, which gives you something like same as before, and that gives you an s greater than equal to n to the single bound. Right? Okay, let me get an estimate. How much time do I have? I don't. 10 minutes? 8 minutes? 10 minutes. Oh, I did not write much. Should at least allow me to finish this one. Yeah. Right. Absolutely. Okay. Good. Right. So so this was just motivation. So let's have just 10 minutes. Let me quickly see as to why this motivating example carries over to shifted partials. Okay, and how we can think of it. So if you observe, there are two things happening here. What this projection is actually doing, each Qij, there was sum of univariates, but there is a big similarity between Qij and Lij. What's that similarity? Lij, each and every monomial in Lij has support 1, but it also has degree 1. In Qij, everything has support 1, degree can be high. So basically what this multilinearity operation is doing is it preserves the support and reduces the degree. That's what it is doing. Okay, so a lesson, what we learned is a projection, the way we defined it, reduces the low support case to the low degree case. That's the lesson. Now, can we use this, and how? So, but for even the question to make sense, I have to first say that when I began the talk, I promised that I will show you a lower bound for general homogeneous depth-4 formulas. There's no guarantee on support or anything there. So to even apply this notion of projection, I have to first show you how to reduce the general case to a low support case. By a low support case, I mean that I want this kind of reduction first. A reduction to, I use a slightly different notation, but close one, curly braces T, which means that so long it was, bracket T, and now curly braces T. Bracket T meant the degrees of each and every monomial in the sparse component inside is bounded by T. And curly braces T means that the support of each and every monomial is bounded by T. So the degree can be high. Is the thing clear? It's basically a sum of something like this, but support of this, each of this, support of every monomial in Qij is less or equal to T. Okay? Now, if I can reduce to this case, then I can probably hope to apply the same kind of multilinearity operation and reduce it to the low degree case as well, because all the higher degree will get killed off by the multilinearity of projection. Okay? So how do I reduce to this case? There is an easy thing which has been discovered many times by many of the other lower bound proofs that we saw by Nizan, Wigderson, and Ranras, and it has been applied. So there's nothing new in this part, and what this part does is the following. It just uses a random restriction. So if you start with a small homogeneous depth-4 formula, if you set each and every variable to 0 with some probability, and if the number of monomials is small, then with very high probability, if a monomial has too much support, it will get killed off. It will go to 0. So only the low support monomial survives. Right? So this is something which has been done. So you just set each and every variable to 0 with certain probability. I'm not going into the quantification of all these things. And the whole formula comes down to this kind of formula. The reason it works is that if you set it to 0 to some appropriate small probability, but think of what happens to the target polynomial. You might have started with some hard polynomial. The claim is, even under random projection, it remains hard. Only then this kind of strategy will work. If you set every variable to 0, then your polynomial might reduce to 0 polynomial, a low degree polynomial, and it becomes tractable then. So your choice of parameter is crucial here. Okay? So I'm just hand waving here. So this reduction can be done using randomized restriction. Now what? So now you can possibly think of, so let me just recall what the shifted partial measure was. It was dimension of, forget about less than equal to, of some polynomial. You want to apply some kind of projection. And the projection that seemingly works is very simple. It's simpler than that map. It takes a polynomial g and maps it to just its multilinear component. That's all. And that's a slightly altered measure of the shift. Oh, sorry, this is x. Yeah. Right. Yep. Right. So this works. Now there is a problem. Yes, intuitively it looks like if you apply a multilinear projection, fine, all the higher degree monomial will get killed off. But you see that you are also multiplying with certain monomials. If you by chance multiply it by a non-multilinear monomial, it will kill it off completely, and it won't give you anything. So this projection comes at a price. You can only multiply it by multilinear degree L monomials. Shift. Okay, so this now has only got to be multilinear monomials. Okay, and the reason it's a problem, do I have a couple of minutes? So the reason this is a slight issue, but fortunately could be circumvented, is because in all the other analysis, whatever Ankit presented and Srikant presented, quite nicely, the L in the earlier analysis was something, it is not right, it was something much bigger than N, asymptotically. It was much, and that seemed to be giving you, some kind of nice advantage. But here you can't. The moment you go beyond N, it will be non-multilinear, and this gives you nothing. So this is the added restriction. And you also recall one common thing between the analysis of what Ankit showed and Srikant showed is that they were basically counting the leading monomials. I'm very much hand waving here. I'm just trying to convey the intuition as to what your analysis gets stuck. So they were counting, in Srikant's case, it was even nicer. The derivative just came to a monomial. So the leading monomial is the polynomial itself. But it's still the leading monomial. But it turns out that, at least, I mean, I don't understand it, that if you just count the leading monomial, it doesn't give you a strong a bound. It gives something. It gives just a quasi-polylower bound for homogeneous depth-4 formula. But it doesn't give this kind of lower bound, which we are shooting for. So it seems that if you just look at, so each of this is a polynomial. By dimension of this, I am saying that you arrange them in a matrix and look at the rank of this matrix. And when I say counting the leading monomial, one way of lower bounding that rank would be just see what are the leading monomials, distinct leading monomials in this matrix. That's one way of doing it. But it seems that's probably not enough for strong lower bound. I say probably because I myself understand whether it will work or not. And at this point, and I learned this from Neeraj, who attributes it to Noga a lot. The beautiful lemma that helps, it's simple but it's quite striking. It just worked for the analysis. And Neeraj showed this, that if B is a real symmetric matrix, then rank of, think of B to be a square matrix. Rank of this is lower bounded by trace of B whole square by trace of B square. Okay? Now, so let me give you the, sorry? Switch the numerator and the denominator. Is it B square by? That's fine, right? So yeah, maybe I'm wrong, but if you give me additional 2 more minutes, I'll try to prove this. So okay, so right, and why does this help? Again, the intuition. How do we get to a symmetric square matrix? See, this is a set of polynomials. This set of polynomials naturally defines some matrix. Need not be a square matrix, and that's your, the entries, the rows are defined by this different choice of derivatives. Each row stands for such a thing, and that's your n. You started with such a such a rectangular matrix, and now the way to go about, you define B to be m times m transpose. That's a square matrix. And the beautiful thing is that no matter which underlying field you are talking about, rank of B is always greater than the rank of M. So a lower bound on this will automatically give a lower bound on this. So why is this? And this is also a linear algebra exercise, because you study the null space. Let's say the null space of M has a vector x. If you multiply both sides, this will go to 0. So naturally B of x is also 0. So null space of this is contained in the null space of this. So, sorry? Oh, wait. Did I read? Okay. Yeah. I was thinking in terms of the null space. Yeah. So the null space of this is contained in the null space of this. That's why the rank is lower. Right? So naturally, if you get a lower bound on this, something here that will automatically give you a lower bound on this. Right? And that's how you apply this lemma. And that's where also this additional constraint comes in the analysis, that it works for characteristic zero field. So one open question would be, can you remove the restriction by some other means of analysis? Up to this much was fine, but this apparently holds only for real symmetric matrix. Okay, and you can make it work for characteristic 0. Okay, so right. So since I don't have time at all, so let me just state a few questions which would be interesting to look at. One would be, remove this characteristic 0 thing. Second thing is that the target polynomial which we used, I think it was never defined in this talk. So the target polynomial is the Nizan-Wigderson class of polynomials which look like this. So it's a polynomial like this. You think of, this goes from 1 to d. You think of the finite field of size d square. You call the elements of that finite field, or just name them as, or refer to them as 1 to d square, where 1 to d is a finite field fd. You just name them like this, so that you. So now you go over all univariate polynomial with degree bounded by some parameter. Call this here h, and the summation is over all choices of such h. Okay? And the inner summation is following. It goes over just the elements of the finite field, which is 1 to d, and does this product. So it's a degree d polynomial. Now what's the nice property of this polynomial? The nice property of this polynomial is, which Srikanth also used for IMM. If you look at two monomials, two distinct monomials, that will correspond to two distinct univariate polynomials in each. And since this degree is bounded by r, they cannot overlap, or they cannot share more than r variables between them. And this disjointness, or almost disjointness among the variables, turns out to be really useful for the analysis to go through. So, yeah, but unfortunately, this polynomial is seemingly much harder than IMM. So the second question would be that, can you prove this lower bound for IMM? That would at least, okay, so if the question is whether you want to separate ABP from depth-4 homogeneous formulas, then I have an answer to this, and the answer is affirmative. Yes, because we could show a quasi-poly lower bound for IMM over any field. So the separation is there, but the ultimate goal is to basically not just show the separation between ABP and homogeneous depth-4, but also higher depths. If luck is with us, probably homogeneous with all of us, then probably homogeneous formulas. So that means that if you are really shooting for a homogeneous depth-4 formula lower bound, where your target polynomial is IMM, then you better show a strong lower bound instead of just a quasi lower bound, if you are hoping to go to higher depths. And right now it's just quasi polynomial, which I think all of us believe is not tight. So that's the second immediate open question which one can be shooting for. And the other obvious third open question is, can we push it to other models? Can we think of other modifications of the shifted partials, or maybe something radically new which will help us? Thanks. Questions? Yes. Sure.
When you consider the measure, you first ground projection and then you do your problem.
Right. Absolutely. Right. So what Amir is absolutely. So what Amir is saying that the actual measure, which since I hand waved so much, it's not just this. You recall we just hit it with a restriction first. So to be very precise, the actual measure is you apply a random restriction first on f, then apply the derivative, then shift it, then apply the projection. Yeah, so right, so that's another good question. So Neeraj showed us this calculation. This really, I like it very much. And so apparently it's not clear, like how can such a trace help us? You have just M, you know just M is your matrix. It turns out, I mean that's easy to see, that since B is defined as M times M transpose, trace of B will be basically the number of non-zero entries in M. So you have reduced it to counting the number of non-zero entries in M. You think of M and M transpose, and the trace of it. So you're only bothered about the diagonal elements. You take a row, ith row here, multiply with the ith column here. And that gives you the number of non-zero entries in that row. So together trace will give you the number of non-zero entries in M. 0, 1 matrix. Because these are all 0, 1 coefficients. And M will only have the coefficients of this target polynomial. So this is a 0, 1 matrix. So that's one nice thing, and you can immediately see that it's looking at the entire M. It's not just looking at the one section of the leading monomial. And this looking inside is more visible in the denominator. It's more visible in the denominator, which, although I haven't calculated, the denominator turns out to be, in terms of M, to be the number of boxes here. Boxes with 4 points, such that all of them are 1. So it's looking deep into the structure of M, at least to some extent. So, and that's what makes me hopeful that maybe it's possible to do it for other target polynomials like IMM, to look deep into the structure and prove something strong. Okay?